we're going to determine if the series, the summation n equals 1 to infinity of sine of 1 over n converges or diverges. Now we're going to use first test for divergence. We're going to try using test for divergence. And recall what that is. Test for divergence says that when we have a series, let's call it a sub n, if the limit as n approaches infinity of the sequence that from which the series is made, so that's limit n goes to infinity of a sub n, and that limit is not 0, so it could be either a number or it could be undefined, then the series diverges. Now what it doesn't say is if the limit is 0, n goes to infinity of a sub n. If that's the case, then test for divergence is inconclusive and it doesn't provide us with anything. We have to try something else. So let's try using test for divergence here. We take limit as n goes to infinity of sine of 1 over n. That's the same, of course, as sine of the limit as n approaches infinity of 1 over n. That's equal to sine of 0, which is 0. And test for divergence is inconclusive. Well, after reviewing all the tests that we learned so far, we're going to try the limit comparison test. Now what is the limit comparison test? I'll abbreviate it by LCT. LCT says the following. Suppose we have two series, the summation a sub n and the summation b sub n, with the restriction that an and bn must be positive for all n. And if the limit as n approaches infinity of an divided by bn is equal to L, with L positive and finite, then we have two cases. Either the summation an and summation b sub n both converge, or the second possibility, they both diverge. So, or summation an series and the bn series diverge. So what we cannot have is the an series converging while the bn series diverges, and vice versa. So we always call the an series the series we're trying to evaluate. So here the summation from 1 to infinity of a sub n will be our series summation from 1 to infinity of sine of 1 over n. Now how do we determine the bn series? Whenever you encounter something like this with a sine or a tangent where test for divergence is inconclusive, you let the bn series be whatever is inside the sine. So in this case 1 over n is inside the sine, and that is what's going to be our bn series. So let's evaluate the limit and see if we can use limit comparison test. We're going to look at the limit as n goes to infinity of sine 1 over n, that's an, divided by 1 over n, that's bn. Now let's rewrite this using x as a continuous function. So both sine 1 over x and 1 over x we can think of as continuous functions over the interval from 1 to infinity. So it's the same as the limit as x goes to infinity, sine 1 over x divided by 1 over x. And to evaluate this limit, we can do one of two things. First, we can use substitution. Let y equal to 1 over x. So note that as x goes to infinity, becomes larger and larger, y becomes smaller and smaller, and it approaches 0. So it actually approaches 0 from the right. So this limit becomes limit y goes to 0 of sine y divided by y. And I hope you remember this fact. This limit is equal to 1. This was derived in an earlier video from Calculus 1. Now we can derive this another way. We look at the limit as x approaches infinity of sine of 1 over x divided by 1 over x, and as x goes to infinity, sine 1 over x goes to 0 and 1 over x goes to 0. So we have this indeterminate form, 0 over 0. So we can apply the L'Hopital's rule, which I'll abbreviate by L apostrophe H, which says that that's the same as the limit x approaches infinity of the derivative of the numerator, that would be cosine of 1 over x times the derivative of 1 over x, which is minus 1 over x squared, divided by the derivative of the denominator, which is also minus 1 over x squared. And as you can see, we cancel minus 1 over x squared. And now, as x approaches infinity, 1 over x goes to 0, and we end up with cosine of 0, which of course is 1, and that's the same as what we had before. So in any case, the limit that we calculated, that is the limit as n approaches infinity of an over bn, in this case, is equal to 1. This is our L. It is clearly positive and finite. So what that says is that the two series, the an series, let's write it over here, that's the summation from 1 to infinity of sine of 1 over n, and the bn series, that's n equals 1 to infinity of 1 over n, both converge or both diverge. But when we look at this series, we recognize this as, of course, the harmonic series. And the harmonic series diverges. And because it diverges, we can now say that the summation n equals 1 to infinity of sine of 1 over n also diverges, and by the limit comparison test. Now let's take a look at a similar series, the summation from 1 to infinity of cosine of 1 over n. Now before we rush to use limit comparison test here, remember how we started the previous problem. We looked at and used test for divergence. So let's try using that here. We take the limit as n goes to infinity of cosine of 1 over n, and we notice again as n goes to infinity, 1 over n goes to 0. Cosine of 0 is not 0, it is equal to 1. Now that's not 0, and we can say that this series diverges by the test for divergence. I'll abbreviate that again by TD. So it diverges by the test for divergence and not by the limit comparison test. For more videos, visit www.mathprepvideos.com.